Good day, everyone. My name is Archel G. Austral, BE Ed student. For today's video, we will talk about developing students' understanding in physics, earth science, and space science under Unit 2. So first, let's tackle about developing students' understanding in physics. So first, in order to develop students' understanding in physics, number one, it requires students' active engagement with the challenge. The learner must engage with the challenge, investing energy in resolving the tension between new and old that challenges has introduced. Over the past half century of research on college effects, the most persistent finding has been that learning is not a spectator sport. As colleague put it, for the turtle to advance, it must first stick its neck out. For learning to occur, students must engage the challenge meaningfully. The higher the level of engagement, the greater the educational benefit. Number 2. Occur in supportive environments. Educationally effective experiences are more likely environments that stimulate exploration, examination, experimentation, and risk-taking where failure is acceptable. Supportive environments provide encouragement and appropriate guidance to help learners and succeed. Support mechanisms mediate the learner's response to a challenge, channeling that response in constructive, educationally effective ways. Whatever its form or origins, support facilitates continuation of the learning or developmental momentum a challenge has sparked. Support does not, however, mean coddling students or dumbing down what is to be learned. It provides whatever the learner needs to engage to the challenge and benefit educationally from resolving the tension the challenge created. Together, a challenge and support make an educationally effective experience possible. Number 3. Encourage active real-world learning. Socrates notwithstanding, the most common teaching approaches today still involve an instructor, lecturing, and group discussions, often led by teaching assistants. For the most part, students play a passive role, learning primarily through memorization and recall. Beginning in the 1990s, active pedagogies began to emerge, capitalizing on students' interests and motivations for learning to involve them in their own and others' learning. For example, working in team and learning from one another. With active learning, students often work on real-world or simulated problems for which no correct answers or solution exist. Experimental approaches are more effective overall and promote such skills as problem identification, critical thinking, evaluating evidence, and alternative ideas, and tolerance for ambiguity. Number 4. Involve other people. Student learning and development may be a solitary activity, like reading, studying, viewing art, or witnessing an event. More often, however, the challenge occurs when the student engages it with others, such as peers or mentors. Some challenges may be more cumulative than catalytic, as when students adopt or reject per group or other values, attitudes, and behaviors. A group may also provide support for resolving challenge-generated conflict. Number 5. Invite or promote reflection. This characteristic has drawn more theoretical than empirical attention, largely because of its multiple definitions, the heterogeneity of the forms and areas of its application, and the process it might entail. According to Matthew G. and other scholars conclude, however, that providing opportunities to reflect is a vital, research-based characteristic of effective teaching and learning. Indeed, reflection is one of the specifications for service learning courses, and one can reasonably argue it inheres in problem-based learning. Living learning communities, diversity experiences, or assisting on a faculty's member research project, all of which have a documented positive effect on learning and development. The case for reflection's centrality in learning and development, however, also rests on logical grounds. Conceptual or behavioral change arguably requires consideration of what new means in the context of current knowledge. Number 6. Involve encounters with challenging ideas or people. Basically, this is Newton's first law of motion in action in the academic, cognitive, psychosocial, attitudinal, and career preparation dimensions of students' post-secondary education. A body will remain at rest or in motion in a straight line unless compelled to change in states or direction by an outside force. In a student's educational life, the outside force challenging the student present ideas, beliefs, perspectives, or educational environments different from those the students hold or can accept. The outside force may also be people who differ from students in significant ways. Whatever its nature or source, in or beyond the classroom, if the challenge is not so minor it is barely noticed, or so overwhelming it is quickly rejected. It opens the door to broader or deeper knowledge, to the reformation of ideas or beliefs, to the adoption of more differentiated and complex understanding. So we are already done on developing students' understanding in physics. Now let's proceed on developing students' understanding in earth science. So during the development of science, knowledge students must also create new concepts and new belief systems which do not necessarily supplant their framework theories but coexist with them. These developments are gradual and slow and follow a learning progression. In order to be effective, science education needs to make students aware of their initiative understanding, provide scientific information gradually and in agreement with students' learning progressions, and develop students' reasoning abilities and executive function skills. In the last 50 or so years, research in science education has provided a great deal of information about how students develop an understanding of science concept. In the pages that follow, I will focus on three aspects of this development: the creation of intuitive understanding, the process of science learning, and the presence of conceptual coexistence. So just like what I've said a while ago, we will focus for now on three aspects of development. So the first is the creation of intuitive understanding. So intuitive understanding, there are three main points of view on this matter. First, known as the classical approach. So it claims that students concepting have the status of utinary intuitive theories, often resembling earlier theories in the history of science. The second approach, known as knowledge in pieces. It claims that students' conceptions consist of multiplicity of phenomenological principles of prisms, which are abstracted from experiential knowledge. So the third main point of view on this matter is the framework theory. According to the third approach, known as framework theory, students' conceptions consist of a collection of beliefs and presuppositions which are organized in loose but relatively coherent framework theories. So the second aspect of the development is the process of science learning. So the position one takes regarding the nature of students' intuitive understandings can have important implications about how one interprets the process of science learning. If students' conceptions have the form of intuitive theories, then the process of science learning cannot be seen as one of a creation or enrichment of prior knowledge. What is needed is instead theory change, or otherwise known conceptual change. Postner et al. 1982 argued that conceptual change requires the replacement of intuitive theories with the correct scientific ones. This replacement was described as the result of a rational process during which students need to become aware of the fundamental assumptions and epistemological commitments that characterize their intuitive theories and to realize their limitations and inadequacies vis-a-vis the scientific theory. Implications for teacher education and professional development. From the perspective of the framework theory, there are three main points that need to be emphasized regarding instruction. First, Science learning is a constructive process that gradually builds on and modifies prior knowledge. Depending on the learner's prior knowledge, learning the correct scientific explanation is not something that happens immediately and suddenly. Rather, it may take some time to be accomplished. There is a learning progression involved. Second, cognitive conflict can be used in the process of learning science, but mainly in order to increase students' metacognitive awareness and understanding of the gap between their existing beliefs and the new scientific information, rather than to prove that intuitive understandings are wrong and need to be replaced. Intuitive understandings are resistant to instruction because they are immediate and common sense interpretations of everyday and experience because they are constantly reinforced by this experience. Last but not the least, science instruction needs to develop students' reasoning abilities, their epistemological beliefs, and their executive function skills. Science learning requires complex spatial reasoning, the ability to take different perspectives, construct complex and abstract models and representations, and inhibit prior knowledge so that new, conflicting information can be entertained. The cultivation of these skills and ways of reasoning should be an integral part of science instruction. So we are already done discussing about developing students' understanding in physics and earth science. Now let's proceed on developing students' understanding in space science. So Earth and space are vast and complex topics. But are they too complex for kindergarten, first grade, and second grade students? No way. Not if we capture their imagination and build on what they know. When we build on students' interest and experience, we can expand even the youngest students' knowledge and build a framework for lifelong learning. Because our format includes interactive activities, games, and hands-on classroom explorations, we're involving students in the types of experiential learning that leads to growth. So why is it important for students to develop their understanding on space science? So it is important for students to develop their understanding on space science because it drives innovation and leads to progress and economic development. It inspires future generations of scientists and engineers, and it drives global information exchange and communication. Space science makes us look outwards from our planet to the stars and beyond. So that would be all for my discussion for today's video. So once again, I am Archel G. Austral, Bachelor of Elementary Education student. References are posted on our description below.